What is reaction at point B? You know it's going to be pointing up, right? It has to be upward pointing. But the question is, what's the value of this?
2p.
Very good. It's 2p. Why is it 2p? Because of force equilibrium. So I'm not going to repeat that part. From force equilibrium, you know it has to be 2p. However, because there's a force P acting at point B, so one of them will be cancelled out. That means you can just treat this whole thing with what? With just 1p at point B. Okay? So we're going to say this. Of course, it's going to be downward. There's a downward pointing P, and the 2 is another upward pointing 2p. So in the end, these 2 becomes just 1. Just 1p. Would you agree? Right? And what else we have? We also have internal moment, correct? And this is what we know as mb. Now, what's the value of mb? We already talked about this. mb is a force times the distance, correct? Now, you please do not confuse that this part to be the whole thing, because from here to here, we know that this is delta C, correct? But the net distance between the force P acting at point C and the coordinates of x2 and y2 is not delta C, but it's delta C minus delta B. Would you agree? So that's why from here to here, this distance is delta C minus delta B, which means what? Which means that MB is actually P times delta C minus delta B. Would you agree? Right? Then we have everything we need to carry out the moment equilibrium. So let's take the moment equilibrium at point B. And you can assume whatever the direction you like. I've been using clockwise to be positive, so let's continue using it. Okay. So what do we have? We have P, right? Do we have any moments at the end? Do we have any moments? At P2, of course, that's the maximum. So we're gonna have, we only have what? This is not actually the end, this is actually it's somewhere in between. Because we are cutting this from, we're cutting that part from here. We're not looking at the whole thing, we're cutting it from this section. That's what we are doing. Use this color, we're cutting it from here. Just like what we did, we cut something from here, right? So the second free body diagram, remember this one here, we use the distance is from the center of the coordinate along the y1 axis. And in this free body diagram, the distance is going to be, of course, when I say this delta C equals delta B, this should be the maximum value when it's at the top. Is that clear? This value here, please be careful. We are not looking at the top. The top is somewhere above this location. We're looking at when we cut somewhere inside here. In other words, the whole column in this section part looks like this. And we establish a reference coordinate system at point B, which looks like this. We said this is y2, this is x2. We know that at the end, right here, you do have delta C minus delta B, which is from here to here. This is true. This part is delta C minus delta B. But our free body diagram is not at the end. Our free body diagram is cut it from here to somewhere between. That's how we cut free body diagram. So even at this point, you will still have this force P. And do we have internal moment? We do, right? We do have internal moment because you cut it somewhere here. You still have internal moment here. This is your internal moment. Once again, we are not looking at the whole thing, which is between point B and point C. So here I should not call it point C, right? Because this point is not really point C. It's somewhere between. So when this free body diagram actually was not properly established when I say this whole thing is point C minus point B. What I meant is at the end, with at point C, it will equal to this value. But if you look at the free body diagram that is somewhere between point B and point C, the horizontal displacement is not going to be delta C minus delta B. Is that clear? Delta C minus delta B is the extreme that's at the end, which is at point B, at point C. Right now, when we cut the free body diagram, we cut only a section of it. So in that case, the horizontal distance is not going to be delta C minus delta B, but it's just going to be variable y2. Okay, so that's why we have M internal plus P times y2. Why is y2? Is because we're not at the end point. We're at from the reference point to whatever you consider, which is this distance. And this distance is the variable y2. Of course, we know that when y2 is at L over 2, this will become delta C minus delta B. That's at the end. So the free body diagram is not at the end, but it's somewhere. You cut only a section of it. And then here, we still have to consider the moment at point B, and that we know is minus mv. The whole thing must be 0. Now, once again, because the curvature is positive in this kind of deformation profile, so you can write it like this: M internal equals the positive of EI times Y2 double prime. So we have Y2 double prime plus P over EI times Y2 equals MV over EI. And we define another variable. We defined K1 before, now let's define K2. So let's call it K2 is the square root of P over EI. This is another definition. Then we can express that one before. However, let's go back to the first one. The first one, remember, we call it K1 is the square root of 2P over EI. So they are not quite the same, right? However, if K1 is the square root of 2P over EI and K2 is the square root of P over EI, what's the relationship between K1 and K2?
Square root of 2?
We can explain that in the next page. This is page 34.
Professor?
Yes.
What happens to our moment at A? We don't carry it over?
No. The moment at A happens only at point of A. Because that has the effect of this P acting at point B. But as you can see that the moment produced by, we have 2 P's, right? I don't want to further confuse you, but for the time being, if you call this one to be M1, and this one to be M2. At this point, when we consider X2 and Y2, there's no effect of P2. And MA actually has the effect of P2. So that's why we don't consider MA here, because MA contains the contribution of P2. But while we are looking at the member BC, there's no effect of P2 because P2 acts at the origin of X2 and Y2. And at the origin, what's the distance? 0, right? To consider the moment effect, you must have force and the distance. But P2 in this coordinate, X2 and Y2, has no distance, it's 0. Only P1 will produce moment, and P2 does not produce any moment. That's why we don't consider MA. Is that clear?
Yes, thank you.
Welcome. All right, and so if the best way is always to write it down, so this way you can clearly figure this out. We know that K1 is K1 squared is 2P over EI, and K2 squared is P over EI. Now, what is P over EI? P over EI is just half of the 2P over EI, correct? So can I say that K1, K2 squared is just half of the K1 squared? Can I say that? Of course, right? Therefore, what's the relationship between K1 and K2? Well, from here, you will already have it. That means K2 is just the square root of 1/2, right? Or you can also say that K1 is just what? It's just the square root times square root of 2 times K2. Either way, right? Maybe you like this expression better. So this is something we can discuss on the side. Just put it on the side. Now, wait. We have found the expression of this. Now we just have to write this. So this is still step 3. And we can write it like this. Y2 of X2 will become, we already use A and B, so here we're going to use capital C times the sine. Be careful, K2 X2 plus D cosine K2 X2. Right? And the same thing, minus, you can write it this way, MB over EI over K2, or you can also write it the other way, which is MB over P. And personally, I prefer the M, there's a square, don't forget about this. Personally, I prefer to write MB over P, because that's easier. So this, of course, the whole thing equals to MB over P. They are the same things.
Why is it negative MB over P this time? For Y1 was positive MA over P.
Oh, it's positive. I'm sorry. You're right. It's positive, right? I carry this whole thing over. It's positive, right? Because it's positive MB. So here the solution is positive.